We present an approach to dock two multirotors in midair using relative pose measurements from computer vision. We use two types of quadcopters in the experiments. A passive quadcopter, which globally localizes itself using a motion capture system and carries a marker at its bottom, and an active quadcopter, which localizes itself relative to the passive quadcopter by seeing the marker using an onboard camera. The active quadcopter obtains measurements from the following onboard sensors: an accelerometer, which measures its proper acceleration, a rate gyroscope, which measures its angular velocity, and a camera looking at the passive quadcopter's marker to measure the relative position and orientation. These measurements are fused together using the extended Kalman filter to estimate its relative position and velocity with respect to the passive quadcopter and its absolute attitude in the inertial frame. The state estimates are then used to command the active quadcopter at a desired set point relative to the passive quadcopter using a cascaded position and attitude controller. The estimation scheme is shown with dashed green lines and control scheme with solid black lines. Using this, we were able to dock the quadcopters in midair repeatably. We compare the docking performance with different sensing schemes. On the left is the midair docking task done using only the motion capture system, and on the right, we show midair docking where the active quadcopter is using purely onboard sensing. Motion capture markers on the active quadcopter for the onboard sensing case are only used for analysis and not for control. We would like to emphasize that the docking task requires a relative position precision on the order of a centimeter, which is consistently delivered by our onboard state estimator and controller.